Welcome back. In this session, we will be looking at differential evolution. Previously, we have studied two other meta-heuristic techniques, teaching learning based optimization and particle swarm optimization. So, in this session, we will be looking into differential evolution. So, this is going to be the outline of this session. First, we will see what is differential evolution. Differential evolution primarily consists of two operations. One is called as mutation and another one is called as recombination. So, we will look into those operators, mutation and recombinant operators. Depending upon minor variation, we have a few variants of DE, we will look into that, and as usual we will take the example of sphere function and we will look into the detailed working of DE, and then we will do a preliminary comparison of the three meta-heuristic techniques that we have studied so far. So, differential evolution was proposed in 1997 by Stone and Price. Ever since then it has been widely used by researchers. So, here as we can see, as time has progressed, differential evolution has been used by a large number of research community. Since meta-heuristic techniques are independent of the domain of the problem, it has been used in engineering, computer science, decision sciences, social sciences, business management and various. Here what we are showing is just a sample of few selected areas. There are various other areas in which differential evolution has been applied. So, this shows the use of the three techniques that we have come across. One is teaching learning based optimization, the second is particle swarm optimization and the third one is differential evolution. So, TLBO as you know was came up in 2011. So, obviously it has been not as widely used as particle swarm optimization and differential evolution, but between particle swarm optimization and differential evolution, particle swarm optimization seems to have attracted more attention than differential evolution. Just like particle swarm optimization and teaching learning based optimization, differential evolution is a stochastic population technique. In differential evolution, each solution is known as genome or chromosome. So, each chromosome undergoes mutation followed by recombination. So, those are the two operators, mutation and recombinant operators. So, there are few terminologies that we need to keep in mind. So, one is target vector. So, target vector is the solution which is undergoing evolution. So, the target vector is used in mutation to generate a donor vector, and the donor vector undergoes recombination to obtain the trial vector. So, between the trial vector and target vector, a greedy selection is employed, right. So, whichever solution is better will survive for the next generation, right. So, here one thing we need to keep in mind is that selection of better solution is performed only after the generation of all trial vectors. So, for example, in TLBO, if we had solution 1, let us say it underwent teacher phase and we obtained solution S1 prime, and it underwent learner phase. Let us say in learner phase we did not obtain a good solution, so we retained S1 prime. So, when we are working with solution 2, if we randomly selected solution 1, then we will be working with this updated member, right, not with this initial member. That is what was happening in teaching learning based optimization. Similarly, in particle swarm optimization, we had a solution 1, we generated its velocity, updated velocity, then we updated its position, let us say S1 prime, and when we were working with solution 2, if we had to randomly select a solution, it is possible that we would have picked up S1 prime because that is updated. As soon as we get a solution, we update a population. That is not the case in differential evolution. So, here we will have, if we have solution 1, we may generate S1 prime, right, but when we are generating S2 or S3, if required we will be using S1, right, and not S1 prime, right. This updation will happen after all the solutions have undergone the mutation and recombinations. Mutation operator is a very simple operation. Here in this mutation operation, we need to select 3 random solutions, right. So, again we have a population of solutions, let us say S1, S2, S3, S4 and so on. So, we are supposed to select 3 solutions randomly and they should not be identical. So, for example, if let us say we select S3, S4, S5, right. So, then we need to apply this equation that the first solution plus a scaling factor which is a user defined parameter. So, it is usually between 0 and 2, the second solution minus the third solution. So, that will give us our donor vector, right. So, in this equation if we see that the solution for which we are generating the donor vector is not at all involved. So, the target vector is not involved. So, when we were generating donor vector for S1, 3 other random solutions help us to generate the donor vector for S1. So, when we are generating a donor vector for S2, 3 other random solution help us to generate donor vector for S2. S1 and S2 are not involved when their donor vectors are generated. So, here if we see that our population size has to be at least greater than or equal to 4, because let us say we are working with solution 1, right, then we need 3 random solutions. So, that has to be 3 different solutions. So, at least this. So, in this case when we are working with S2, the 3 other random solutions would be S1, S3, S4. So, here we need to keep in mind that we need 3 random solutions and they should not be equal, right, and the target vector itself does not participate in mutation. Once we have completed mutation, the next step is to apply recombination. So, recombination is applied to increase the diversity of the population, right. So, here let us first understand the terminologies, right. So, here uj indicates the jth variable of the trial vector, right. Vj indicates the jth variable of the donor vector, and xj indicates the jth variable of the target vector. This crossover which we are studying is known as binomial crossover or uniform crossover, right. So, in this the target vector takes part in the recombination operator, right, whereas that was not the case in the mutation operator. So, here if we see that the trial vector is going to have variables which are coming either from donor vector or target vector. We are not going to calculate anything as such, right. It is just that we need to pick a variable either from the donor vector or from the target vector. These are the 2 conditions which will help us to decide if a variable has to be picked up from the target vector or from the trial vector, right. So, we have this user defined parameter known as crossover probability PC. So, in addition to crossover probability, we will have to randomly select a variable within the number of decision variables. So, if capital D denotes the total number of decision variable, we will have to select an integer between 1 and d. So, let us say if we have 10 variables 1, 2, 3, 4 and so on up to 10, then delta is to be generated randomly for every solution. So, let us say delta is 5, right. So, this j will run from 1 to 10 and delta is a randomly generated integer for every solution that is undergoing this crossover operator, right. So, if this condition satisfies, that if r is greater than the crossover probability and j is not equal to delta, right, then in that case the target vector's value is taken into the trial vector. Else if this condition is satisfied, that if the random number is less than equal to PC, then the mutant vector's value is taken into the trial vector, right. So, here if we see, here there is an OR condition and here there is an AND condition, right. So, if we see for one variable j which is equal to delta, so here we are going to modify each and every variable, right. So, for the jth variable, right. So, for example, del is equal to 5. So, this j is going to vary from, this equation holds for j equal to 1 to all the way up to the number of decision variables, right. So, in one case we are going to meet this condition where j is going to be equal to delta, right. So, in that condition, no matter what is the crossover probability, this equation would not be used, but this equation would be used, right. Over here we have an OR condition. So, irrespective of the crossover probability, the value is going to come from the mutant vector, right, for the variable j is equal to delta. So, that is what we discussed, that the del ensures that at least one variable is obtained from the donor vector, and probability for crossover is generally high. If it is high value, then most of the random numbers which we generate will be less than PC. Most of the values for the various decision variables will be coming from this mutant vector and not from the target vector. So, let us see an example, right. So, let us say there are 5 decision variables and we have generated a random number delta is equal to 3 and let the crossover probability be 0.8. So, let us assume this is our target vector x1, x2, x3, x4, x5 is our target vector, whereas our donor vector is given by v1, v2, v3, v4 and v5, right. So, now the question is how do we generate our trial vector, right. So, since there are 5 variables, we need to generate 5 random numbers. For the first variable, the random number is 0.9, second variable it is 0.5, third variable it is 0.85, fourth variable it is 0.91 and fifth variable it is 0.25. So, we have generated 5 random numbers corresponding to 5 decision variable. Delta value was randomly chosen, right, between 1 to the number of decision variables. So, in this case it is 3. So, this u1 to u5, right, these values are not known. X1, X2, X3, X4, X5 are known because that is the target vector. We applied the mutation operator. So, we also know V1, V2, V3, V4, V5. Now, the question is which of these values from the target vector or the donor vector would come into the trial vector. So, that is again governed by this equation which we have given over here. So, let us see for the first variable what would happen. So, for the first variable the crossover probability is 0.8, right, whereas the random number is 0.9. So, 0.9 is greater than 0.8. So, this condition is satisfied, right, and j is not equal to delta. So, j for this variable is 1 because it is the first variable. So, the second condition is satisfied, right, and the first condition is not satisfied. 1 is not equal to 3, right. So, this OR condition is not satisfied and the random number is also not less than the crossover probability, right. So, this condition fails and this condition is satisfied for the first variable. So, x1 value is to be taken as the first decision variable in the trial vector, right. In the second case, random number is 0.5, our crossover probability is 0.8, right. So, in this case what will happen is R is less than PC, right. So, for the second case R is less than PC, this condition is satisfied, right. So, it will come from the donor vector. So, the value is going to come from the donor vector. So, for the third case the random number is 0.85, whereas the crossover probability is 0.8. So, 0.85 is greater than 0.8. The first part of the third condition is satisfied, 0.85 is greater than 0.8, right, that is satisfied. However, j for this is 3, for this variable j is 3 because it is the third variable. So, this second condition fails, right, that j should not be equal to delta, whereas now delta is also 3 which we had randomly selected initially and the value of j is also 3. The second condition fails despite the random number greater than being PC, right. So, in that case the first equation is to be used. In the first equation, remember this part is again not satisfied, R is not less than equal to PC, right, but this is a OR condition, right. So, since this is a OR condition, this part of the equation is satisfied, that j is equal to delta. So, this value comes from the mutant, right. Similarly, we can see for the fourth variable. So, j is not equal to delta and 0.91 is greater than 0.8. So, it is going to come from the target vector. So, the random number for the fifth variable is 0.25, right. So, it satisfies the first equation, right, 0.25 is less than 0.8, right. So, it will come from the mutant vector. So, this should be V5, right. So, this is how the trial vector is generated, right. For the trial vector, the values we are going to take either from the target vector or from the donor vector, depending upon the crossover probability and the delta value which we have randomly chosen. We will be deciding whether the value comes from the trial vector or from the target vector. And so, this is another example, right. So, here in this case instead of x1, x2, x3, x4, x5 we have taken the value. So, this is what is going to happen when we are working with a problem, right. So, this is the target vector and this is the donor vector, right. So, the target vector, donor vector is given, the trial vector is what we are trying to find out, and we have generated random number between 0 and 1 for all the variables, right, and the delta value which we have generated randomly is 4 and the crossover probability is 0.8. So, if we apply this equation, so in the first case R is less than equal to PC and j is not equal to delta, j for the first variable is 1, right. So, the value is going to come from mutant vector or the donor vector, right. So, the donor vector has a value of 23. So, that value 23 is to be taken over here. In the second case, R is greater than PC and j is not equal to delta because PC is 0.8, R value which we have taken is 0.91. So, in this case the value, the second condition is satisfied, right. So, if the second condition is satisfied, the value is to be taken from the target vector. The value of the second decision variable is 43. So, for the third variable r is less than equal to Pc because 0.79 is less than 0.8. So, the third variable is going to come from the donor vector. For the fourth variable we have 0.9, right. So, this condition is satisfied, 0.9 is greater than 0.8, but this condition is not satisfied, that j is equal to delta. This we can use only if j not equal to delta, right. So, this equation we will not be using it. The value will not come from the target vector, but it will come from the donor vector, right. So, similarly we can find out for the rest of the variables. So, for this fifth variable r is less than Pc, right, because r was 0.25. So, 0.25 is less than equal to Pc, then it is going to come from the donor vector. For the sixth case 0.85 is greater than 0.8 and j is not equal to delta, because j for this is 6 and the delta value which we have taken is 4. Right. So, it is going to come from the target vector. Similarly, you can perform for the rest of the two variables and we can generate the entire trial vector. Right. So, this is the binomial or the uniform crossover. So, we have looked at a mutation strategy, we have looked at a crossover strategy. There are two types of crossover, one is the binomial crossover and the other one is the exponential crossover. In a little while we will look at the exponential crossover. So, one of these crossover is to be used. So, the first step in differential evolution is to take a solution, generates its donor vector. So, for generating its donor vector we will require 3 other random solutions which should not be identical, right. So, that way we generate the donor vector. Once we have generated the donor vector, we need to apply the crossover to generate the trial vector. So, after generating the trial vector, we need to check whether the trial vector is within the bounds of the decision variable or not. So, this is something similar to particle swarm optimization. In particle swarm optimization, we generated the velocity, but we did not check whether the velocity is within the bounds, right. After generating the velocity, we generated the position and it was the position for which we checked whether it is in the bounds of the decision variables or not. So, similarly over here, the donor vector may or may not be in the bounds, right. It is not to be bounded because the donor vector is subsequently going to be used to generate the trial vector. So, it is the trial vector whose bounds have to be checked, right. So, the first step is to employ mutation to generate the donor vector, then we need to apply the uniform crossover or the exponential crossover to generate the trial vector, and then we need to check whether the trial vector is within the bounds or not. So, the bounding strategy which we have discussed in particle swarm optimization and teaching learning based optimization is the corner bounding strategy. So, the same strategy is employed in differential evolution, right. So, here if we see if the variable is within the bounds, let us say the lower bound is 2, the upper bound is 5 and the variable is, if the variable value is 3, right. So, we do not need to bound it because it is already in the bounds. If the lower bound is 2 and the upper bound is 5 and if we get a value of 8, then it has to be pushed back to the upper bound, right. So, x nu is being pushed to the upper bound. Similarly, if the lower bound is 2, the upper bound is 5 and we get a value of 1, then the decision variable will be pushed back to the lower bound, right. So, this is the bounding strategy which we are employing so far. So, the same bounding strategy will be employed in differential evolution to generate the trial vector which is in the bounds. So, once we have generated the trial vector, the next step is to evaluate the fitness function value. So, in this as we explained earlier, right. So, if we have 10 solutions S1, S2, S3, S4 all the way up to S10, right. So, for each solution a donor vector is to be generated and for each donor vector a trial vector is generated, trial 1, trial 2, trial 3 and so on, right. So, here we will have a different this thing. So, here donor 3, trial 3, again donor 4, trial 4 and all the way up to all the trial vectors have to be first generated and they should not be updated, right. The updation happens only after we have generated trial vector for all the solutions. So, for example, when we are generating for S4, if we are to pick solutions randomly from the population, we are supposed to pick from this S1 to S10 and not from T1 to T10 or D1 to D10. The solution update will happen after generating all the trial vectors. Once we have generated all the trial vectors, right, then we need to do a greedy selection between S1 and T1, whichever vector is better or whichever solution is better will survive. Let us say between S1 has an objective function of 2 and T1 has an objective function value of 8, and let us say we are solving a minimization problem. So, between this 2 and 8, 2 would be selected. For the next population, S1 will be the first member, right. So, for example, S2 is let us say 5 and T2 let us say it is 3, right. So, in this case T2 will survive, right. So, similarly we will find out between these 10 comparisons we will get 10 solutions. That solution will form the population for the subsequent iteration. That completes the discussion of differential evolution. Consolidate whatever we have seen so far to generate a pseudo code for differential evolution. So, for differential evolution we need to provide the fitness function, the lower bound, the upper bound, the population size, the termination criteria, the scaling factor which is to be used in mutation, and the crossover probability which is to be used in the recombinant operator, right. So, scaling factor has to be between 0 and 2, and crossover probability, as the name indicates, it is a probability. So, it has to be between 0 and 1, right. The first step is to initialize a random population and evaluate its fitness. So, this is common to all the two other techniques which we have studied, right. Then we begin the iteration loops. A set of steps have to be repeated for t times. So, again here we are taking that the number of iterations is a termination criteria, but it can be any other termination criteria also, right. So, then the next step is to perform mutation for all the solutions. So, we have this for loop, right. So, this is our mutation loop, right. So, for I is equal to 1 to NP. So, each member is going to undergo mutation. We need to generate the donor vector, right. So, the donor vector is going to be generated using 3 random solutions XR1, XR2 and XR3. This Vi indicates that for each solution in the population we generate a donor vector. Once the donor vector is generated, we will perform crossover to generate the offspring, right. So, this is for all the variables. We need to decide whether the value of the jth decision variable in the trial vector will come from the donor vector Vj or will it come from the target vector Xj. Once that is done, then we need to bound the solutions. Each of this ui is to be bounded, right, and we need to evaluate the fitness function of it, f of ui and f of I. So, the first target vector will be compared with the first trial vector. Whichever wins will go to the next iteration or next generation, right. So, that is what whichever wins will be updated as population member 1, right. So, between target 2 and trial 2, whichever wins will be updated as the second member of the population. This we have discussed multiple times in this presentation. So, here if we see, this is the generation phase and this is the selection as well as the survivor stage. So, if we see, this also fits into the generalized scheme of meta heuristic techniques which we have discussed earlier, that we have a selection operator, we have a variation operator and then we have a survivor operator. Here selection was done randomly, variation was done using crossover as well as mutation, and the selection was done using a greedy selection strategy. So, here if we see, for every member we do one functional evaluation, right, in this phase, and this happens for NP times, right. So, for every member we will be evaluating the fitness function value. So, this will be NP t times, right, because this one single functional evaluation is inside this termination loop, right. So, the total number of functional evaluation required over in this for loop section is NP into t, and we require initial NP evaluation of the functions in the initial stage before we begin the iterations. So, the total number of fitness function values is given by NP plus NP into t. So, this if we compare with particle swarm optimization, this is similar to particle swarm optimization. In particle swarm optimization also, for every member in one particular iteration we had to do one functional evaluation. So, for NP members we need to do NP functional evaluation, for T iteration we will have to do NP into T times, and then we have the initial NP evaluations, right. So, this number of functional evaluation in particle swarm optimization as well as in differential evolution is same. So, what it means is that if we take a population size of 10 and if we take a number of iteration as 100, right, then the total number of functional evaluation can be given by 10 plus 100 into 10. So, this will work out to 1010. So, if we take a population size of 10 and if we are to perform 100 iterations, we will have to evaluate the objective function 1010 times. So, that completes the pseudocode of differential evolution, right. So, it is a very fairly simple technique if we see, right. First is we need to perform mutation and then crossover. So, this is to be performed for each solution. In mutation we do not require the target vector to participate, right. So, mutation is done with the help of randomly selected solutions from the population. So, in crossover we generate the trial vector. So, the values of the trial vector will come either from the donor vector which we had obtained at the end of mutation, or it will come from the target vector, right. So, once we have generated the trial vector, we need to bound the trial vectors so that it is in the bounds of the decision variables. We need to evaluate their fitness function values. Once we have evaluated their fitness function value, we are in a position to do a greedy selection, right. So, whichever solution is better between the target one and the trial one survives to the next generation. So, this is done for all population members. So, one crucial difference which we are repeating time and again is that the update will happen only after all the trial vectors are generated. In exponential crossover, we will have to first randomly choose an integer between 1 and d, where d is the total number of decision variables in our problem, right. So, once we have generated n, we need to copy the nth variable from the donor as nth variable of trial vector. So, if there are 10 variables and let us say n we have taken it as 7. So, the 7th variable of donor will be directly copied as 7th variable of trial vector, right. For the subsequent variables, we need to generate a random number between 0 and 1, right. So, we need to keep doing this till we encounter this condition r is greater than p c. So, technically we do not need to generate random number for every decision variable, we need to generate only till this condition is met, that random number is greater than crossover probability, right. So, if the random number that we generate is less than equal to crossover probability, we will copy the variable from the donor to the trial vector, right. So, here it is from donor. If the random number is less than or equal to PC, we will copy it from the donor. If it is greater than PC, right, not only that variable, but all the remaining variables will be copied from the target to the trial, right. So, first time we encounter this condition that the random number is greater than PC, we do not need to subsequently generate any random numbers for generating the trial vector. All the variables from the target vector will be copied to the trial vector. So, let us see an example, right. So, this is our target vector. So, this is known. For this target vector, a donor vector was generated. So, this is known. So, the values over here are known, x1, x2, x3, x4, x5 are crisp values which are known. Similarly, v1 to v5 are also known, right. We do not know what will be the trial vector's value, right. So, to determine the trial vector value, we will have to first generate an integer between 1 and 5, because we have 5 decision variables. Let us assume that the random number is 2, right. So, for the second variable, so we need to start from the second variable, right, it is directly copied from the donor vector. For the third variable, we need to generate a random number. If the random number is less than equal to PC, we need to take the value from the donor vector to the trial vector. Subsequent to that, we need to generate another random number, right. If that happens to be less than or equal to the crossover probability, we need to copy from the donor vector to the trial vector, right. Then we need to move on to the next variable. So, in this, for the fifth variable, let us assume that the random number which we are generating is actually greater than the crossover probability. So, in this case what we need to do is we need to start copying from the target for all the variables which are yet not filled. So, this variable is yet not filled and this variable is yet not filled, right. So, we need to copy x5 from the target vector and x1 also from the target vector, right. Now, let us look at an example for exponential crossover. So, let us take an 8 variable problem, right, and we need to generate a random integer between 1 and 8. So, let us say we generate a random number between 1 and 8 as 3 and let the crossover probability set by the user be 0.8, right. So, this is our trial vector. We need to decide on what are the values that would come to the trial vector, either from the donor vector or from the target vector, right. So, if n is equal to 3, that particular variable is to be directly copied from the donor vector, right. So, in this case n is equal to 3. So, we are going to start over here. So, for this variable, for the third variable, no random number is to be generated, it is to be directly copied from the donor vector, right. So, this is our donor vector and this is our target vector, right. So, 4 is directly copied and then we need to generate a random number, right. So, let us say that the random number is 0.86, whereas our crossover probability is 0.8, right. So, this condition fails, right, that r is less than or equal to Pc fails, right. So, since it is failing, all the rest of the values, so u4, u5, u6, u7, u8, u1, u2 which we have not determined so far are to be directly copied from the target vector. 9, 6, 3, 5, 4, 2, 8, all of them are directly copied from the target vector, because we fail to satisfy this condition r is less than equal to Pc for this variable. For the fourth variable, this condition failed, right. So, all the variables are to be copied from the target vector, right. So, this is one case which can occur. So, for the second case, this would be our target vector, this is our trial vector and this is our donor vector, right. So, in this case again let us assume that we start with 3 and our crossover probability is 0.8, right. So, in this case 4 would be directly copied, no random number is to be generated, right. For the second variable, let us say we generate 0.7. So, since we generate 0.7, that is less than equal to Pc. So, it is to be copied from the donor vector. For the next variable, let us say we generate 0.3 as the random number. So, it is also less than Pc because our crossover probability is 0.8. So, 7 is to be directly copied here. Again, for this sixth variable, we need to generate a random number, right. Let us say it is 0.4. So, again we need to copy it from the donor vector. Let us say for the fifth variable, the crossover probability is 0.5. So, it is again to be copied from the donor vector because r is less than Pc is satisfied, right. For the next variable, let us say the random number is 0.9 and our crossover probability is 0.8, right. So, here the condition fails. The condition fails and we still are to fill 3 values u1, u2 and u8. So, all these 3 variables are to be copied from the target vector, right. So, 4 to 8 are directly copied from the target vector. So, what we need to remember is, once we hit a failure, that once the r is greater than the crossover probability, whatever values are yet to be filled are to be copied from the target vector. So, we do not need to generate random numbers after we meet the first failure of r greater than Pc, right. After that, no random numbers are generated. So, here if we see, we did not generate a random number for 2 and for this 8, or the first variable and the second variable we did not generate, because once this condition occurs, all the variables are to be copied from the target vector, right. So, this is another example in which n is 6 and the crossover probability is 0.8, right. So, the sixth variable is to be directly copied, right. For the seventh variable, let us say what we have random number is 0.6 and crossover probability is 0.8. So, this again will come from the donor vector, right. So, this is donor, this is trial and this is target, right. So, this condition is satisfied. For the next variable, random number is 0.2. So, that is also less than Pc. So, it will come from the donor vector. Now, we have come to the end of all the decision variable. So, again we need to start from 1, right, and generate a random number. So, let us say we generate 0.7 which is less than 0.8. So, we will copy from the mutant or the donor vector, right. So, here let us say the random number generated for the second variable is 0.9. So, here we fail, right. So, now we have encountered a failure. So, all these 4 values u2, u3, u4, u5 will have to come from the target vector, right. So, here we are not again generating random numbers, right. So, this completes our discussion on exponential crossover. If you carefully analyze, either it is binomial crossover or it is exponential crossover, one variable will always come from the donor vector. There are few variants of DE, right. So, those variants are generally represented by this common format DE/X/Y/Z. This X indicates something, this Y indicates something, and this Z indicates something, right. So, depending upon what mutation strategy we are using, what crossover strategy we are using, this X, Y, Z are to be filled, right. So, here let us say look at this one. So, DE, so that stands for differential evolution, right, /rand, right. So, this rand indicates the solutions which we are selecting for the donor vector. So, for the donor vector, if you see, we are selecting these 3 solutions randomly, right. We are not saying that it is the best solution or the worst solution or it is the mean solution or anything, right. So, it is selected randomly. So, this rand indicates that thing, right, and this 1 indicates the difference, right. So, here we have one difference between 2 randomly selected solution. So, this indicates 1, right. So, let us look at the second one. So, D again stands for differential evolution. Here it is best. So, here 3 solutions are not selected randomly, but only 2 solutions are selected randomly, right. And for the third one we use the best solution. So, that is why it is called as DE/best, right, and there is only one difference between 2 randomly selected solutions. So, this one stands over here, right. And then we have DE rand. So, obviously rand means that whatever is selected is to be selected randomly for the mutation operator, right, and here we have 2. So, 2 indicates there are 2 differences. So, we have one difference over here. So, this is a difference between a randomly selected solution and this is another difference randomly selected solution. So, if we are to apply this strategy, right, DE/rand/2, then we need 5 randomly selected solutions 1, 2, 3, 4, 5 to generate a donor vector, right. So, the next variant is DE, again stands for differential evolution. We are using best, right. So, it is the same as the previous one, except that we are using the best over here and there are 2 differences. So, this 2 indicates the number of differences. So, we have one difference over here and one difference over here. So, again this is a difference between 2 randomly selected solutions, this is a difference between 2 randomly selected solutions, right. Here the donor vector is generated using the best, right, and 2 differences of randomly selected solutions. So, when we say 2 differences, obviously we need 4 randomly selected solutions, right. So, the last one is DE target to best, right, and one difference between randomly selected solution. So, in all these 4 strategies, if we see, we have not selected the solution which is undergoing the mutation, right. So, we did not select the Xi solution, right. So, in differential evolution, if we are going to employ this strategy for mutation, DE/target to best/1, right. So, this indicates the solution which is undergoing the mutation phase, right. So, it did not appear in any of the 4. This difference, right, is not between randomly selected solutions, but between best and the ith member which is undergoing the mutation phase, right. So, that is why this target to best, right, and then we have one random difference. So, it is 1, right. So, X can take either rand, best or target to best, right. Rand means all the solutions required are selected randomly, best would indicate that the best solution is involved, right, and target to best would indicate that we have one difference which is between the best and the target, right. So, that is what X would stand. This Y would indicate for how many differences are there? Are there one difference or are there two differences? When we say differences, remember it is the differences between randomly selected solutions. So, for example, in this case we have a difference between best and the target, but still we write 1 over here. There are two subtractions agreed, but only one of this is between randomly selected solutions. So, this y can take 1 or 2, and this z indicates the type of crossover we are using. Are we using exponential crossover or binomial crossover, right? So, we have this 5 strategies, let us say with uniform crossover, right. Similarly, we can have 5 more strategies with exponential crossover, right. So, basically if we talk in terms of number, we have looked at 10 variants. 10 variants which depend upon whether we select random solution, best solution or target to best. How many differences do we take? Do we take one difference or two difference, and whether we take exponential crossover or binomial crossover. So, if you analyze this, right, so in this case we need 3 random solutions, right. So, obviously if we need 3 random solutions, we require the minimum population size to be 4. In this case we require 2 random solutions. So, in that case the minimum number of solutions that we require in the population is 3. Here we have 5 randomly selected solutions, right. So, including the population member which is to undergo mutation, we will require 6 members in the population. Here again we have 4 randomly selected solutions. So, the population size has to be at least 5, right. In this case we require only 2 random solutions. So, the population size has to be at least 3, right. So, 2 random solutions, so the population size is 3, right. So, number of random solutions plus 1 gives the minimum population size, right, because the member which is undergoing the mutation phase is not participating in the mutation, right. So, for example, for particularly in this 4 it does not participate. So, xi is not there, only in this case xi is there, but even in that case we need xi, xr1, xr2, right. So, we still need 3 solutions over here. So, those are the mutation strategies in differential evolution. Now that we have looked into differential evolution, let us take the same example which we have used for teaching learning based and particle swarm optimization, right. We will take the sphere function with 4 decision variables and see the working of differential evolution. So, that will help you to clear some of the concepts which we have discussed so far. So, here we have 4 decision variable x1, x2, x3, x4. The decision the domain of the decision variable is between 0 and 10, right. The objective function is the sphere function, which is sum of square of all the decision variables, right. So, the first step is to fix the population size. It is a population based technique. So, we need to fix the population types. We will take the number of generations as termination criteria, and then we need to fix the crossover probability and the scaling factor. So, these 4 are user defined parameters. In addition to this, we also need to specify the type of technique we are going to use crossover, right. So, here we will be using binomial uniform crossover. So, the next step is to generate a random population. So, in this case we have generated 5 random solutions within the domains and evaluated its fitness function, right. So, the next step is to determine the donor vector for the first solution, right. So, this is our target 1, target 2, target 3, target 4 and target 5, right. We need to determine the donor vector for this. Once we have the donor vector, we will be able to determine the trial vector. From target vector to determine the donor vector, we need 3 random solutions, right. So, 3 random solutions we need to pick. In this case, let us assume that the 3 random solutions are fourth solution, second solution and the third solution, right. So, if we pick that, we can apply this equation, right. The fourth solution is 2149 and the crossover factor we have taken it as 0.85. The second solution is 3197 and the third solution is 0315. So, if we apply this equation, we will be able to determine the donor vector. So, this is the donor vector corresponding to the first solution, right. Remember, this solution is not to be bound. So, what we have now done is we have only completed the mutation of the target vector. Mutation for the target vector we have completed. So, we have this donor vector. To apply that uniform crossover, we need to generate d random numbers, where d is the number of decision variable. In our case d is equal to 4, we have 4 decision variables. So, we need to generate 4 random numbers between 0 and 1. So, let us say these are our random numbers. Let us see the application of uniform crossover on the first target vector, right. So, this is the target vector that we are currently working with. So, that is what is written over here 4018, and these are the 4 decision variables, j is equal to 1, j is equal to 2, j is equal to 3 and j is equal to 4. To apply this crossover, we need to have this delta which is a random number between 1 to the population size, right. So, right now we have taken delta to be 1, right, and for every target vector we need to have a random number, because that is what we are going to compare with the crossover probability. So, let these 4 be our random number which we have previously seen, and this be the donor vector which we have obtained from the mutation operation, right. So, now we have our target vector, we have the donor vector, we have the random numbers which will be used to compare with the crossover probability, and we also have this del value. We have everything in place to apply the binomial crossover to determine the trial vector, right. So, we need to see whether the first value of trial vector is going to be 4 or 4.55. The second value in the trial vector is going to be 0 or minus 0.7, the third value is 1 or 10.8, and the fourth value is 8 or 10.7, right. So, that is what we are going to determine. So, first let us check this condition, right. So, since this condition is r is less than equal to PC, so let us say which of this actually satisfy it, right. So, except for the second one, all the three other random numbers 0.3, 0.2 and 0.6 are actually less than our crossover probability, which is 0.8, right. So, that is why we have put this 3 tick marks. So, now that is done, right. So, obviously, if r is less than equal to PC, right. So, for these 3 variable we can directly say that the value is going to come from the donor vector 4.55, 10.8 and 10.7. Without further checking anything, we can actually conclude that we are going to get 4.55, 10.8 and 10.7. right, because for all of them this condition is satisfied, right. So, to check this condition we need to see whether j is equal to delta or not, right. Let us do that. So, now let us see if delta is equal to j or delta is not equal to j, right. In our case delta is equal to 1, this holds because delta is also 1, j is also 1, right. In other cases j is 2 over here, j is 3 over here and j is 4 over here, right. So, for the sake of completion we have given this entire thing, otherwise you do not need to checking this condition for the first variable, third variable and fourth variable, because they are directly satisfying r is less than PC, right. So, this is satisfied. So, here it is the opposite condition, right. So, delta is 1, j is 1, right. So, this is delta not equal to j. So, delta is actually equal to j. So, just for this variable we have this cross mark, otherwise we have this 3 tick marks, right. So, as we said earlier, 4.55, 10.8 and 10.7 are directly going to come from the donor vector. For this case the value of r is 0.9, right. So, r is greater than PC, right, r is 0.9 and PC is 0.8, right. So, in that case we will have to take the value from the target vector 0, right, and it also satisfies this condition that j is not equal to delta, j is equal to 2 for this row and delta was 1. So, this is how we generate the trial vector, right. Once the trial vector is generated, we need to evaluate its fitness, but before evaluating its fitness we need to check for its bounds. In this case the bounds for the decision variables are 0 to 10, right. So, we will have to check which of these variables violate. So, the third and fourth variable actually violate the bounds, right. So, using the corner bounding strategy we will bring it back to the upper bound. So, our new trial vector is 4.55, 0, 10, 10, right. Remember we should not bound the donor vector, because donor vector is not going to be used to calculate the fitness, we will be only using the trial vector to calculate the fitness, right. So, it is not necessary to bound the donor vector. So, after generating trial vector 1, right. So, here we are not showing you the detailed calculation, you can calculate it. So, this is what we have got for the first target vector, right. For the second one the target vector is 3197 and we need to choose 3 random variables between 1 and d, right, for mutation. So, we have taken the fifth solution, the first solution and the third solution, and we have applied this formula to calculate the donor vector. Once the donor vector is determined, we need to generate 4 random numbers because we have 4 decision variables. So, in this case we have taken 0.3, 0.2, 0.6, 0.4, and also we need to generate a value of delta which should be between 1 and random number. So, in this case we have taken it to be 4, right, and then we need to apply this condition to determine the trial vector. So, in this case if we see, so 4.4 is coming from the donor vector because this is 0.3 and our crossover probability is 0.8. So, we are taking it from there. Similarly, we need to find out all the other variables, right, and then bound it. So, this solution which is shown over here is bounded trial vector, right. So, if you do the calculations, you will be able to generate the trial vector. After generating the trial vector, you should check for the bounds, right. So, similarly, if we do for the rest of the 2 solution, this is what we get, right. So, we started with target vector, we generated the donor vector with the help of this equation, right, and then again we generated the trial vector using this equation. So, now this trial vector is bounded, we can evaluate the fitness for each of this. So, the fitness is nothing but for the first solution it is 4.5 square plus 0 square plus 10 square plus 10 square, that will give you 220.70, right. Similarly, the fitness for all the solutions is to be determined, right. So, what we have is initially we started with this population P and this was the fitness. What we now have is U, which is the set of trial vectors and its corresponding fitness function value, right. So, now what we are supposed to do is we are supposed to perform a greedy selection and update the population. So, the new population is going to be, we are going to compare this 81 with 220.70. So, whichever solution is better will go to the next iteration. So, this is the first solution. Between 140 and 114.16, 114.16 survives, right. So, this solution is taken, right. This solution becomes the second solution over here. Between 35 and 171.17, 35 the solution with the fitness function 35 survives. So, this 0315 will be taken as our third solution. For the fourth solution this is 102, this is 16.82, right. So, 16.82 is better. So, this will be our fourth solution. Similarly, over here for the fifth solution 78 is better than 130.7. So, this 1283 will come over here. So, this is our new population. So, this is the population for which we will generate the donor vectors again and the trial vectors again. Similarly, we will bound this trial vectors, evaluate its fitness function and then do a greedy selection. So, here when we applied greedy selection, if we see the solutions over here, this solution 114.16 is actually bad than this 102, yet 114.16 has survived because of greedy selection, right. 114.16 we compared with 140, we did not compare it with 102, right. So, that is why 114.16 is able to survive, whereas 102 is not able to survive because 102 was compared with this 16.82. So, remember it is not like stacking all the fitness function and selecting the best 5 solutions. We are not selecting the best 5 solutions, we are performing a greedy selection, right. So, greedy selection will help us to determine which is better among 2 population members. So, here in this case we are not combining F and FU and selecting the best 5 solutions, right. We are doing 1-to-1 selection. So, that is how we update our population. So, if we continued performing that at the end of 10 iterations, this is what we will get, right. So, here if we say iteration versus best fitness function value, in each iteration if we see it is monotonically decreasing. So, it started with a value of 35 and then it started decreasing, right. So, if we perform few more iterations, we might be able to get this globally optimal solution of 0. At the end of 10 iterations with these settings, differential evolution was unable to get the globally optimal solution. So, this completes our study of differential evolution. Now, we have studied 3 meta-heuristic techniques, right. So, let us make a comparison between those 3 meta-heuristic techniques, right. So, the 3 techniques which we have learnt is teaching learning based optimization, particle swarm optimization and differential evolution, right. So, teaching learning based optimization, if you remember, it was a two-phase algorithm, there was a teacher phase and a learner phase, right. So, here we call it as two-phase because a solution S1 was converted to S1 prime, like let us say we generate S1 prime, if it is better we retain S1 prime, and then S1 prime was used to generate S1 double prime using the learner phase, right. So, there were two phases in which we were updating one particular solution, right. A solution can potentially get updated twice in the same iteration, whereas in particle swarm optimization and differential evolution we say that there are no phases, right, but in particle swarm optimization we have a position and velocity update, whereas in differential evolution we have mutation and crossover. In all the three techniques the convergence is monotonic, right. In TLBO if we see, it is a greedy selection strategy that a solution is discarded only if a better solution is coming into the population. So, that ensures this monotonic convergence. In particle swarm optimization, whether the solution is better or not, it enters the population, right, but we also keep track of the personal best and the global best. Since we always keep track of the global best, even if the best solution is getting discarded from the population, a copy of it will be in the G best, right. So, that ensures monotonic convergence. And differential evolution also, we employed a greedy strategy wherein we compared the target 1 with trial 1, right. So, this trial 1 enters into the population if and only if it is better than this target 1, right. So, that way we do not lose track of the best solution which we have so far. So, parameters if we see, we in TLBO we had only two parameters to be set, like the user had to set only two parameters, one was population size and the other one is termination criteria. In all the three cases we have considered the termination criteria to be the number of iterations, whereas in particle swarm optimization we need to provide the population size, the termination criteria, inertia weight and the acceleration coefficient C1 and C2. In differential evolution we need to provide population size, termination criteria, F, right, and also we need to select what variant we are supposed to use, right. So, the various variants that we had seen was one is with respect to the crossover, right. We can either use uniform crossover or we can use exponential crossover, and there were 5 mutation strategies we had seen, right. So, we need to select one of those mutation strategy. So, in a way that is also to be defined by the user, which mutation variant is to be selected and which crossover is to be selected, that is to be given by the user. So, while generating a new solution in teaching learning based optimization, in the partner phase we randomly selected one partner, in the teacher phase we used the mean and best solution, right. So, that is how we generate a new solution. In PSO we generated a new solution using the velocity vector, the personal best and the G best, whereas in DE we took, except for that one variant where we take best, the other variants randomly take solutions from the population to generate a new solution, right. In teaching learning based optimization as well as in differential evolution, the best solution is part of the population, right. The best solution is inside the population. That need not be the case in particle swarm optimization. So, that is one crucial difference between TLBO, DE and PSO. So, in TLBO there are two places wherein a solution can get updated, the teacher phase and the learner phase, whereas in particle swarm optimization we only update the position once for one population member in one iteration, and similarly in DE we generate one donor vector and one trial vector for every member, right. So, that is why we have two updates in TLBO and one update in DE and particle swarm optimization. So, the selection strategy in TLBO was greedy, right. Same thing in differential evolution, the selection strategy is a greedy selection strategy, whereas in particle swarm optimization the new solution was always accepted into the population. So, number of functional evaluation, in all the three cases it is deterministic. The technique is stochastic, but the number of functional evaluation is deterministic. Deterministic because once we fix T and NP we can uniquely determine the number of functional evaluation. So, in TLBO since there are two solution updates, we will have to evaluate the function 2 NP times in one iteration. So, the total number of functional evaluation which we have previously stated is NP plus 2 NPT, whereas in particle swarm optimization and differential evolution, the number of functional evaluation for a particular member in a particular iteration is only once, right. So, if we have NP members, we will have NP evaluation in one iteration, and since we perform T iterations, the total number of functional evaluation is NPT. We have another NP functional evaluation for the initial population. So, the expression is NP plus NPT, right. So, this gives a quick comparison between the three meta-heuristic techniques that we have studied so far. For differential evolution, you can look into these papers, right. So, this is the paper which proposed differential evolution. Subsequently, there have been various development. This is also adaptive differential evolution, right. So, here they modified the basic differential evolution. A new variant was proposed based on differential evolution, right. And then this is recent advances in differential evolution you can obtain from this paper. So, this article talks about review of differential evolution. With that, we will conclude this session on differential evolution. Thank you.